Bismillah ar-Rahman ar-Rahim. Alhamdulillah wa salatu wa salam ala Rasulillah. Today we're going to discuss the stability of control systems. The objective is how to design the controller in this section or in this method. We will learn how to design the controller, the proportional controller K, for stability, only for stability. Okay, we discussed that. We started with the stability last lecture when we check the characteristic equation. Okay, we check the characteristic equation. We solve for the root. We check the real part of the root. If the real part is negative or zero, that means the system is stable. If it's positive, that means the system is unstable. So our job when we design the controller for stability is to make sure the real part of the root of the characteristic equation is negative, okay, negative, or zero at least. All right. Now, we always start from the characteristic equation, right? We always start from the characteristic equation and we solve for the root. Now, we have a problem if the characteristic equation, like this one, is of an order n higher than 1, for example, or higher than 2, like to the power 3, 4, 5. The problem is that we cannot solve for the root easily without a computer, right? It's going to be very difficult. Okay. So what we do? All right. Now, this is the topic of today's lecture. One method called Routh criteria. One method called Routh criteria. What is Routh criteria? Routh criteria is developed by a scientist or engineer. His name is Routh, back in the 19th century. Okay, he created this method. This method is very helpful to determine whether you will have a unstable root in your characteristic equation without solving for the root. You don't have to solve for the root. This is the objective or the idea of Routh criteria. Okay. All right. How it works? Let's assume we have this example. This is the characteristic equation. S to the power n, S to the power n minus 1. And these a's are the coefficients, okay, of the characteristic equation. All right. Routh said it is necessary but not sufficient condition for stability that all the coefficients a's must be non-zero and positive. Okay. So the first step in using Routh criteria is to check the coefficients of your characteristic equation, these coefficients. If they are all positive, if they are all non-zero, they do exist, okay? Non-zero, positive, non-zero. What does that mean? Is the system stable or unstable? The answer is maybe stable, maybe unstable. You have to go to the next step, which is we call the Routh Array, and I will show you to you in a second. Okay, but this is a first step toward your checking the stability of the system. So you check all the coefficients. They must be non-zero, non-positive. If it's one of the coefficient is equal to 0, or one of the coefficient is equal to negative, that means the system right away you can say the system is unstable. There must be an unstable root. Okay. Otherwise, you have to go to the next step. What's the next step? Next step is to build the Routh array. We call it the Routh array. It's like a matrix. Okay. Now I will show you how to do it. Okay. It's all about calculations. Okay. All right. How you build the array? The first column, this one, you start with s to the power n minus 1 until you go to the s to the power 0, which is equal to 1. Okay. In the first row, you start with the first coefficient. Then you skip the next one and go to the third coefficient. Okay, this one. Then you skip and go to the fourth coefficient, and so on. In the second row, you start with the coefficient that you skipped in the first row. So you start from here. Then skip the next, go to the next. Skip and go to the next, and so on. So the first and second row, you don't have to do any calculation. The calculation will start in the third row. The calculation will start here. This coefficient will equal this coefficient times this one minus this coefficient times this one. Second, and divide by the first one that you started with. This is for B1. For B2, you will do the same, but you will multiply by the next coefficient. So an minus 1 times an minus 4 minus an times an minus 5. And always you divide with the first coefficient that you started with. Okay, so the division will be the same, the denominator. All right, and until you reach number 0, until you get 0, you stop. Then the next one, you will do the same thing, except you will start with the coefficient in the previous row. Okay, that's all. All right, and so on. Until you reach 0, you stop. I will show you next example, and it will be easy, inshallah. Okay, this is the example. But before we start the example, there are rules. These are the rules of the Routh criteria. You have like 5 rules. Number 3 and number 5 are the most important rules that you will use in your stability analysis or the designing for the controller. You will use number 3 and number 5. These are the most important rules. Okay, now let's assume you build a row. This rule says if you have any sign change in this column, the first calculated column, that means you will have instability in the system. You will have at least one positive real part root. If you have one positive real part root, then the whole system will become unstable. All right. Number 5, this is very important. The number of sign changes in this column, indicate the number of unstable roots, the roots with positive real parts. Remember, if you have at least one unstable root, the whole system will become unstable. Okay? But if you are interested to know how many unstable roots, then you have to check how many sign changes in this column. All right? Now let's see this example. Inshallah, it will be easy. Okay? Now, this is your characteristic equation. This is the characteristic equation of a system, control system. All right? All right. Now, is this system stable or unstable? This is the question. Okay? Is system stable or unstable? I don't know. I have to solve for the root. Can you solve for the root using the analytical method? It's not easy, right? You need a computer. So what we're going to do, we're going to use Routh criteria. How to use the Routh criteria? Condition number 1. Okay? Condition number 1. Okay, this is very important. You have to check all the coefficients. Okay, so number 1 is all coefficients, or the A's, these coefficient, here, this one, this one, this one, this one, this one. Is all, or are all coefficients, more than one, are all coefficients greater than or equal to 0? Check. We have s to the power 4, right? It's number 1. So this is positive, non-zero. Good. S to the power 3, positive, non-zero. S to the power 2, positive, non-zero. S to the power 1, positive, non-zero. S to the power 0, this one also S to the power 0, positive, non-zero. So the answer is yes. Good. Checked. What did he say also? All coefficients must be non-zero and positive. So this is the first condition, okay? This is the most important condition. If yes, is the system stable now, stable or unstable? You don't know. You have to build the Routh array. You have to build the Routh array, and then you can decide whether the system stable or unstable. Let me ask you this before we start building the or calculating the Routh array. Let me ask you this question. What if one of the coefficient is missing, okay, equal to 0? So this is 2s to the power 3, 4s to the power 1, and 5. There is no coefficient here, okay? This is my characteristic equation. Is this system stable or unstable? The answer is the system is unstable. How do you know? By checking the first condition for Routh criteria. One of the coefficient is equal to 0. Okay, so that means the system is unstable. You don't have to build the Routh array. You can say right away there must be at least one unstable root. The system is unstable. You got it? All right. Another example. Okay. Another example. All right. What if this coefficient is not, or this one, let's change this one. This is negative 2, not positive, negative 2. This one, negative 2. So this one positive, negative, positive, positive, positive. Is this system stable or unstable? The answer, the system is unstable. It's not stable. Why? Because one of the coefficient is negative. So according to Routh criteria, the system must be unstable. There must be at least one unstable root. So the whole system becomes unstable. You got it now? I hope so. All right. All right. Okay, let me erase this before we start. Okay. All right. All right. Now this is the first condition. Okay, all the coefficient non-zero and positive. That means the system may be stable, may be unstable. We have to build the array. How to build the array? Start with the highest power, s to the power 4, s to the power 3, s to the power 2, s to the power 1, s to the power 0, the last one. Okay? All right. Now for the first row, it's very easy. You start with the first coefficient, number 1. This one, number 1. Then you skip number 2, go to the number 3, number 3. Then skip number 4, go to number 5, number 5. Then you stop. Okay, you stop here. All right, next row, you start with the coefficient that you skipped earlier. So you start with the number 2. Then skip number 3, go to number 4. Then skip number 5, nothing here. So what does it mean nothing here? That means it's 0. If you get 0, always you stop, okay? You always stop at 0. Halas? All right. Now let's go to the next row. This is the first calculation we're going to do. How much is this coefficient? It's going to be number 2 times number 3 minus number 1 times number 4. Divide by number 2. Halas? It's going to be equal to 1. All right. Next, this one. How much this one? You always start with the first one. Number 2 times, not number 3, number 5. Skip. Minus 1 times 0. Divide by 2, the one you started with, always. It's going to be equal to 5. What about here, this one? What about the coefficient here? This coefficient will be 0. How do I know it's going to be 0? Because it's going to be number 2 times nothing here, 0. Minus 1 times nothing here, 0. So it's going to be 0 here. So you stop, huh? Once you get 0, خلاص, go to the next row. All right. What about this one now? This one will be 1 times 4 minus 2 times 5 divide by number 1 that you started with. And it's going to be minus 6. Okay, what about this one? This one will be 1 times 0 minus 2 times 0. And it's going to be 0. Once you get 0, خلاص, you stop here. Go to the next row, which is going to be the last row. All right, this one. It's going to be minus 6 times 5. Minus 1 times 0. Divide by minus 6. It's going to be number 5. All right. What about this one? This one, minus 6 times 0. Minus 1 times nothing here, which is 0. Okay. Nothing here, 0. So it's going to be 0. Then you stop. خلاص, you're done with the Routh array. Now we start the analysis. خلاص. Now, all the analysis will be on this column, the first calculated column. Everything is here. Okay? Is this system stable or unstable? The first question. Okay? The system. My question is, is the system stable or unstable? Answer. You have to check this column. Any sign change in this column, any sign change, that means the system is unstable. There must be at least one unstable root. So check. This is positive. Positive 1. Okay, positive 1. Positive. Positive. Okay, sorry. Okay, positive. Negative. You see? So there is a sign change. What does it mean, sign change? So the system is unstable. خلاص. At least there must be at least one unstable root in the system. How do I know? This is using Routh criteria. This is his theory, okay? His criteria. خلاص? All right. So this is to check whether the system is stable or unstable. Question number two. Okay. If I ask you how many unstable roots in this system, how many unstable roots, then we're going to use this rule. The number of sign changes in the column, in the first column, indicate the number of unstable roots, the roots with with positive real part. Okay, so let's check. This is positive, 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 negative. So this is number 1. Sign change, okay? Number 1, sign change. Okay. Then back to positive, this is number 2. So how many sign changes did I change in this column? Once here and once here. So the total is 2. So how many unstable roots? That means there are 2 unstable roots. Okay, that means with positive real part. Okay, this is what I mean by unstable root, positive real part. خلاص? So that's all. Okay, this is how we use the Routh criteria. All right. Let's go to the next example. All right. This is the last example for this chapter, and this is the first example for you guys to start designing the controller. We want to design the controller for stability. So you see here, we have a controller here. How do I know there is a controller? There is K here. This is the proportional controller, huh? This is the proportional controller. Okay, or the gain. We call it the gain also. Like the volume of the radio. Okay, like the volume of the radio. So for example, this is the characteristic equation of a system, control system, like a radio in your car, for example, the radio of your car. And this gain represents the volume of the radio of the car. The volume of the radio of the car. Okay, I ask you, I want to sell this radio. Okay, what is the range for K for stability? If it's possible to stabilize the system, what is the range for K for stability? Okay, all right. If this is to the power 2, then we can do just solve for the roots. But this is to the power 3, so we're going to use Routh criteria. Okay, so first condition for Routh criteria, check all the coefficients. Are all coefficients positive and non-zero? This one positive, non-zero. Is to the power 2, positive, non-zero. Is to the power 1, positive, non-zero. Is to the power 0. This K depends. This is our design. So the first condition we must pick, K must be greater than, 0. Not equal to 0, greater than 0, and positive. Okay? So this is the first design for K. K must be always greater than 0. خلاص? All right. We need more information about K, so we're going to build the Routh array. S to the power 3, S to the power 2, 1, and 0. First row, you start with the number 1, skip number 3, go to 10, skip number K, there is nothing here, so you end up with 0. Now, in the second row, you start with 3, skip number 10, go to K, skip nothing there, so it's going to be 0. I'm going to start calculation from here, right? This coefficient will be 3 times 10 minus 1 times k, divide by 3. This coefficient here will be 3 times 0 minus 1 times 0, so it's going to be 0. Then you stop, go to the next row. All right. This coefficient will be the number, the resulting number here, times k, minus 3 times 0, divided by this number, which after calculation is going to be k, by the way. If you evaluate this, it will be k. All right. This number will be the number here again, times 0, minus this number times 0, nothing here, 0. So it's going to be 0. Then you stop. Halas, we're done. Okay. This is the Routh array, we call it. All right. Now for stability analysis, we will check the first column. Remember, for the system to be stable, there must be no sign change in this column. There must be no sign change. What does that mean? This is positive. Positive. So this one must be positive. So 30 minus k divided by 3 must be what? Positive, right? And this k also must be positive. So this one must be positive, and this one must be positive. Okay? So this one must be positive, and k must be positive, which is the same as the conclusion that we got earlier, right? Both of them. There must be k. So we need to solve this one. If you solve this one, this will give you what? If you solve it, this will give you 3 times 0. This will be k less than 30. Okay? Therefore, k must be less than 30. K must be greater than 0. So the k range must be between 0 and 30. Okay? So k range, this is the conclusion, the answer. K range for stability is from between 0 and 30. In between, huh? Between 0 and 30. Between 0 and 30. Okay? So what does that mean? That means, again, if this is the characteristic equation of the radio you want to sell, okay? What's the volume? This is the K represent, for example, the amplifier or the volume of the speaker, okay? So what can you tell the client, the range, the feasible range or the possible range for the volume or the gain or the amplifier? It must be between 0 and 30, right? So if you pick the volume, for example, this is the volume, between 0, the maximum must be how much? 30, right? Right? Okay. So if you pick 30.1, what will happen to the system? It will become unstable. You will damage the amplifier. You will damage the speaker, for example. Okay? All right. If you pick 0, also it's not good. It's not going to work. It's going to be unstable. 0.1, okay. 29.9, okay. 30, not okay. Okay, you got it? So this is the last example for Routh criteria. Inshallah, next lecture, we will start with a more sophisticated method. The Routh criteria, this is the general picture of designing the controller. If you want to design the controller for accuracy and settling time, all the other aspects of the transient response, we're going to use the root locus, okay? Remember, this method is only for stability. However, when we build, inshallah, next lecture, when we start talking about root locus and designing the controller, we will design only for stability. In this course, we will focus only on stability, okay? So thank you for listening and see you, inshallah, next lecture.